720 million years ago, the Earth was much different than the one we inhabit today. A massive supercontinent called Rodinia contained nearly all of the landmass on Earth, surrounded by a global ocean. The atmosphere contained oxygen, methane, carbon dioxide, and water vapor. However, the arrangement of the continents was causing a process of increased weathering to occur, leading to the entrapment of greenhouse gases, and a long period of global glaciation that we now call Snowball Earth. In 1992, Joseph Kirschvank proposed a theory that the Earth was once entirely covered by a thick sheet of ice, pointing to some paleomagnetic evidence in glacial diamictites that showed they formed near the equator. This theory was immediately met with controversy, as many scientists refused to believe that such widespread glaciation was even possible. Since that time, further evidence has been uncovered suggesting a global glaciation, such as cap carbonates, indicating a slowdown in photosynthetic activity, and glacial dropstones in equatorial regions. In the modern day, the Snowball Earth theory is widely accepted, but there remain major debates around the causes of it. Did the evolution of photosynthetic life forms deplete the world's supply of greenhouse gases? Or did volcanic and tectonic activity contribute to cataclysmic changes in the composition of the atmosphere? Today, we explore those questions.
The climate of early Earth was very different from that of today. During the Hadean, the Earth was extremely hot, following millions of years of celestial bombardment. However, this hot Earth runs counter to a theory called the Fate-Young-Sung paradox. In its infancy, the sun was weaker and released less energy than it does today. Due to this weaker sun, many scientists believe the Earth could not have sustained year-round intense heat. However, this theory fails to account for the greater proportion of greenhouse gases found in Earth's atmosphere. Earth would not be able to sustain life unless its atmosphere changed drastically.
The Great Oxidation Event is key to understanding the state of the atmosphere preceding the Cryogenian period. Before the atmosphere contained a large enough amount of oxygen to sustain complex life, it was composed mainly of nitrogen and carbon dioxide. Early cyanobacteria existed and were busy producing oxygen, but that oxygen was being depleted by reactions with dissolved iron in the oceans, creating banded iron formations that are famous worldwide. Many speculate that this supply of dissolved iron was slowly running out, and eventually the oxygen being pumped out by cyanobacteria was being released as free oxygen instead, contributing to the Great Oxidation Event. However, others believe that the GOE was caused by the appearance of a number of large igneous provinces, pointing to their easily weathered mafic compositions as both sources of dissolved iron in the ocean, thus stopping photosynthesis, and contributing to the burial of carbon dioxide through weathering.
In early Earth, there were no tectonic plates. Earth went by a process called single-lid tectonics. In planets with single-lid tectonics like Mars and Venus, rather than a system of moving plates, all the excess energy in the mantle is released through plumes. Around 3 billion years ago, Earth experienced a transitional period from single-lid tectonics to the system we call modern plate tectonics. This shift was brought about by the creation of massive fissures that expanded and eventually gained the capacity to create new crust and recycle the old crust. This new tectonic regime eventually created the supercontinent we call Rodinia.
Okay, so just as a little demonstration of how single-lid tectonics works, we've got this big pot of soup. You can see here, if I spin it a little, it's got sort of a film on top of it. That's a lot like a lid. It's one piece covering the whole thing. Now, when I turn the heat up, like I have here, you'll see it's going to start bubbling. And when those bubbles come through, they're going to make little cracks in this, much like fissures or plumes in the mantle. Alright, it's bubbling pretty good. We should see it start to crack through in just a second. Oh, I see one right down there. Alright, nobody's breaking through yet. Alright, we can see it starting to almost break through there. It's a lot like the process that would have cracked this into multiple plates.
Rodinia was a large supercontinent that existed from around 1.1 billion years ago to 750 million years ago. Scorched and barren of large life forms, the landmass is easy to dismiss as unimportant to the development of life in the climate. However, weathering processes acting on its rocky surfaces created large beds of sedimentary rock and eventually some thin areas of soil. These weathering processes filled the oceans with minerals as fluvial processes eventually led them to the ocean. Those minerals helped to feed the life forms in the shallow parts of the sea with nutrients, allowing for a great variety of single-celled organisms to thrive.
It was previously thought that the first multicellular life forms to colonize the land did so during the Ordovician period, about 200 million years after Snowball Earth had already ended. However, in recent years, evidence has been uncovered, suggesting that simple fungi and lichens could have colonized the supercontinent Rodinia long before the global glaciations began. These recent discoveries have led to new theories about the cause of the increased weathering that triggered Snowball Earth to begin. If fungi and lichens, both highly effective at weathering rock, colonized the pre-cryogenian land surface, they could have weathered the rock rapidly and caused a significant amount of carbon dioxide to be captured and stored in long-term sinks. The mechanics of the carbon capture that triggered global cooling are hotly debated to this day. Some biologists claim that the carbon dioxide could have been used up and processed by cyanobacteria, and that the dead cyanobacteria precipitated to the bottom of the anoxic ocean as marine snow, allowing chemosynthetic, iron-reducing bacteria to consume them, producing carbonate minerals as waste products.
Okay, so here's a little demonstration of how carbon burial by organisms could have worked in the times leading up to the cryogenian. So let's say we're on the land surface and we have some blueberries here representing carbon-bearing minerals. And let's say that rain and weathering bring some of those into the ocean. Now, what lives in the ocean? Cyanobacteria, represented by these raspberries. And so cyanobacteria could take up the carbon in those carbon-bearing minerals, and then those would float on down to the deep ocean, where they would be eaten by iron-reducing bacteria, represented by me.
Opponents of this theory claim that carbon was buried through tectonic processes. The increased weathering on continental surfaces deposited calcium carbonates in the ocean that were then buried by the new process called subduction, which began with the initiation of modern plate tectonics. Though this process is slow, the interior of the Earth is one of the largest carbon sinks available, and subduction burial could have captured trillions of tons of carbon.
We know that life could have colonized the land before Snowball Earth began. But how did that life survive the brutal freezing conditions of the cryogenian Earth? We can look at modern examples of extremophiles for a clue. In Antarctica, we can find large gatherings of microorganisms called microbial mats. These wide-reaching mats remain dormant for much of the year, but during select seasons they spring to life, performing some of the most efficient photosynthetic processes seen in any living organism. It has been suggested by some in the scientific community that cyanobacteria could have survived in veins or pockets in the ice, seasonally coming out of a long slumber to perform rapid photosynthesis.
There are several overlapping lines of evidence that help us understand the timing and rate of Snowball Earth's final melting. One major clue comes from the stratigraphic record. Sediments deposited around 635 million years ago show a rapid continuous sea level rise between 15 and 75 centimeters per year over roughly 6,000 years. Another key line of evidence comes from cosmic dust. During global glaciation, cosmic dust entering Earth's atmosphere gradually settled on the ice sheets. When the glaciers eventually melted, the dust sank to the sea floor and became part of the sediment layers. By taking cores of the sea floor, researchers have identified distinct accumulations of cosmic dust dating back to around 635 million years ago. Another study measured Earth's past climate using oxygen isotopes and marine rocks. The measurements showed a rise in global temperatures between 635 and 580 million years ago. Together, the rise in sea level shown in the stratigraphy, the accumulation of cosmic dust, and measurements of Earth's past climate allow us to constrain the most recent deglaciation to around 635 million years ago, with a major melting period lasting around 6,000 years.
Ultimately, the question of whether tectonic or organic processes caused the initiation of Snowball Earth likely has an answer somewhere in the middle of the two. Living organisms likely contributed to the rapid weathering of tropical Rodinia, and combined with the massive carbon capture power of the anoxic deep ocean and subducting plates, depleted the atmosphere of essential greenhouse gases. Finding a real satisfactory answer to the question, what caused Snowball Earth, will require greater interdisciplinary collaboration, something that many research institutions are hoping to pioneer. Historically, there have often been wide chasms between scientific disciplines like biology and geology, but increasingly, we are seeing an explosion of excellent teamwork between these communities. I'm certain that, as interdisciplinary collaboration becomes more widespread, we will see not only the answer to the Snowball Earth question, but countless other lingering questions about Earth's history and beyond.